Okay, so good evening all. Today we will, we have almost finished GATE 2019 paper also for inorganic part. If you people have any problem from like till 2019, you can ask me. So today we will start with question number 14, which came in GATE 2018 chemistry paper. So the question is, the water exchange weights for the complex ions follow the order. There are three metal complexes given. So all the metals here are transition metals. Okay, so one is this vanadium aqua complex, like vanadium with with six water. One is cobalt complex, and the other one is chromium complex. So we have to find out that what is the water exchange rate for this for the given complex ions. So for finding that water exchange rate, what we should know that if a complex is inert, okay, if a complex is inert, then it will be like less willing to exchange water, right? So first of all, what does water exchange means? It means that there is, like, let's take this vanadium complex. So vanadium is having six water, okay, six water and 2 plus state, it is there. So if we add, let's say, y number of water ligands where this oxygen is labeled oxygen, okay, that is either 17 or 18 isotope of oxygen. From this, it will be vanadium H2O 6 minus Y and H2O, the labeled one will be Y again, okay. So this type of reactions are known as water exchange reactions. Okay. So it depends on the kinetic stability of the complex ion given. Kinetic stability. So the complex can be either inert or labile. Okay. This inertness, now we will take the three complexes which are given in the question. Okay. So one is vanadium H2O whole 6 2 plus. The other one given is cobalt H2O whole 6 2 plus and chromium H2O whole 6 3 plus. Okay, so these are the three complexes which are given in the question. So first of all, we will first write down the electronic configuration for this. Like here, vanadium is how many electrons, how many d electron system? Valence shell electron configuration, anyone?
D1.
Okay, so it is no, it's not D1. Scandium, titanium, vanadium, right? 3D series.
I was telling related to oxidation state.
Due to oxidation state, it will be D3, right? Because
Okay,
from
okay,
H2 it will
okay.
go. So vanadium 2 plus means it will be 3D3. So it is a D3 system. Okay. Then moving on to this cobalt complex. So CO is D7, right? So here also it is in plus 2 oxidation state. Why? Because we know that water is a neutral ligand. It does not carry any charge. So if we consider X as the oxidation state of cobalt, then X plus 6 into 0 is equal to plus 2 or X is equal to plus 2. Okay. So here also cobalt, it is in plus 2 oxidation state. Here vanadium is in plus 2 oxidation state. So it is a 3D7. So it's a D7 system. Then moving on to chromium. Chromium's electronic configuration, it is 3D5 4s1. Okay. So now here what is the oxidation state of chromium?
Plus 3.
Yeah. So chromium is in plus 3 oxidation state. That means it is Again, this is also a D3 system, right? So this is again a D3 system. Now here there are 6 water ligands. So all these complexes which are given in the question are octahedral. All of them are octahedral complexes, and we know that in an octahedral crystal field, the 5 degenerate d orbitals split into two sets, which are T2G and EG, right? 3. So this is T2G and this is EG. Now for the 3 complexes, one was for vanadium, it was D3 system. For chromium, it was D3 system. And for cobalt, it's a D7 system. Now if we fill the electrons, okay, these are the T2G and EG orbital sets. So in T2G there is dxy, dyz and dxz, whereas in EG we have dz squared and dx square minus y square. So let's fill the electrons in the d orbitals. So D3 means this will be the thing, and for chromium also D3, whereas for cobalt 2 plus there are 7 electrons. Now we know that water is a weak field ligand. Okay, so since water is a weak field ligand, so this complex will be high spin or low spin. Anyone?
High spin, ma'am.
Yeah. So it will be a high spin complex. That's why. Okay. So here 7 electrons will be like this: 1, 2, 3, 4, 5, 6, 7. Now we also know that, as I said, that this will depend on the kinetic stability of the compound. So whether it is inert or labile. If there is, like in an octahedral crystal field, what happens is that there are 5 types of d orbitals, right? So the ones, sorry, it's not proper. So the orbitals which are present between the axes, that is dxy, dyz or dxz, they are, if we consider this as x and y, then this is dxy orbital. Okay. So if we consider this, then one system is this, which makes the T2G, and the other 2 orbitals are like this. One is gx square minus y square. Okay, so here x and y if we consider, and the other one is dz square. Okay, so this is also along axis. In an octahedral crystal field, always a ligand, it approaches from the axis. Okay, so now if we see dxy, dxz and dyz orbitals, then in this case, for these 3 orbitals, the orbitals they are lying in between the axes and not along the axis, whereas for dx square minus y square and dz square orbitals, the orbitals are lying along the axis. So therefore, whenever any electron will be present in dx square minus y square or dz square orbital, the repulsion will be more. Okay. So therefore, if there is any electron present in the Eg orbital, any electrons present in Eg orbital, then that complex will be labile in nature. Okay. And also the complexes in which there is vacant space in T2G orbital as well. Like if it is a D1 system or a D2 system, in those cases also it will be labile complex, because here is space for electron to come, right? The T2G orbital is also vacant. So D1, D2 and wherever electron is present in Eg. Okay, electron in Eg orbital. These complexes are labile in nature, whereas the others are not. So if we now look onto these complexes which are given in this question for vanadium and chromium, we can see that these are D3 systems. So can anybody tell me this is a inert system or labile?
Inert.
Okay. So these two are inert, whereas for cobalt case, we can see that there are electrons present in the Eg orbital. So this is a labile system. So from this we can, like, now we can say that cobalt will have the maximum rate of water exchange, right? Now we have to compare between vanadium and chromium. So how to compare between them? We know that when like the oxidation state is more, like this is the inertness is inversely proportional to the charge or the oxidation state of metal. So we have seen that if the oxidation state of a complex is more, then the delta O value also increases, which is the crystal field splitting between the two orbitals, that is G2G and Eg here. So that value also increases if the complex is in higher oxidation state and it becomes more inert in nature. So these two we can compare on the basis of their oxidation state. So here vanadium is in +2 oxidation state, whereas chromium is present in +3 oxidation state. This means that chromium is more inert, chromium 3 plus is more inert than vanadium 2 plus, and therefore we will get this order, that is chromium will have the least, this chromium aqua complex will have the least water exchange rate, followed by vanadium aqua complex, and the maximum water exchange rate will be observed for the cobalt aqua complex. So in the given question, that is the water exchange rates for the complex ions follow the order. Chromium will have the least, followed by vanadium and then cobalt, right? So this will be option number D is the correct option for this question. Is this clear? Hello?
Yes, ma'am, clear.
Okay. Is it clear to everyone? Okay, then we will move on to the next question. That's question number 50. So next we will discuss question number 15 from GATE 2018 paper. So the question is, the lowest energy DD transition of the complexes follow the order. So we have to write the order of the, like, energy of DD transitions for these complexes. So again, this is a question from coordination chemistry. Okay, and here they are asking about the energy. So the complexes given are chromium H2O whole 6, chromium NH3 whole 6, and chromium CN6 3 minus. So we will first write the complexes. Chromium hexa aqua complex. In this chromium is in plus. Okay, if this complex is having a charge of +3, then chromium NH3 whole 6 +3 and chromium Cn whole 6 3 minus. Okay, and the question is the lowest energy DD transition of complexes. Now again, here in all the cases there are, we can see that there are 6 ligands. So this is an octahedral complex, and as we discussed in the earlier question as well, that in an octahedral crystal field the degenerate d orbitals are splitted into two two sets. One is G2G and the other one is EG. Okay, so 3. This is T2G and this is EG. And the difference between these two sets is delta O, or the energy difference. This is the crystal field splitting value for octahedral complexes. Now, more is the gap between these two. That is, the more is delta O, higher del O means high energy DD transition. Okay. So higher del O means high energy DD transition. And these type of questions, like as now we have solved many problems, we know that mostly in every paper, in paper of each year, there is one question which comes from spectrochemical series. So here also what we have to see that delta O value depends on three parameters, depends on three factors. So the first one is oxidation state of metal or charge of metal. The second one is the principal quantum number, that is 5D metals will have more delta O value than 4D, than 3D. And the third one is the ligand field strength. Okay, so now if we compare these three complexes, here in all the three cases, the metal is chromium, which is a 3D element. So we can't compare these three complexes on the basis of this parameter 2. So we will cancel out this. The first parameter is oxidation state of metal. So let's find out the oxidation state for these three complexes. If we consider the oxidation state of chromium as X, we know that H2O is a neutral ligand and it carries the charge of 0. So for this one, X plus 6 into 0 is plus 3. So what is the oxidation state of chromium? Plus 3, right? Now again for this complex as well, ammonia is also a neutral ligand and it carries 0 charge. So here also X plus 6 into 0 is plus 3, that is X is equal to plus 3. So in this case as well, chromium is present in plus 3 oxidation state. Now for this complex, the cyanide complex, X plus cyanide carries a charge of, like, which charge, anyone?
Negative.
Yeah, so one negative, right? And the overall complex charge is minus 3. So x minus 6 is minus 3 or x is equal to plus 3. So in all the three cases, the oxidation state of chromium is plus 3. So we can't compare these three on the basis of oxidation state of metal as well. So we can see that in the three cases, the ligands are different. In one, the ligand is H2O, and in the other two cases, one is ammonia and the other one is cyanide. So we have to compare on the basis of ligand field strength, and we will know that by the spectrochemical series. Spectrochemical series. So we know that as per spectrochemical series, the compounds, the ligands in which carbon is the donor, like CN, CO, for these type of complexes, they are high field, followed by the ligands where nitrogen is the donor atom, followed by oxygen, and followed by X, that is halide. Okay, so we can remember the spectrochemical series in this way also. It will be easy to remember
Please repeat it.
this spectrochemical series. So see, like for complexes like in which carbonyl is the ligand. Okay, so here C is the donor. So for ligands where carbon is the donor, like CO or CN type of ligand, for them they will lie in the higher region. Okay, so they are strong field ligand, whereas halides are weak. So a general way to remember this, you can remember this in this way. Okay, weak field. Like first, it will be the carbon ligands in which carbon is the donor, then where nitrogen is the donor, then oxygen, then X. So example of where nitrogen is the donor is NH3, oxygen is donor is water, right? Water or O2 minus type of ligands, and X is halides. So that's why what will happen is, if we are having a strong field ligand, then we know that the delta O value increases, right? So here, if we compare the complexes which are given here, in one it is water, other it is ammonia and Cl. So here, if we see cyanide, then ammonia, and the other one is water because their oxygen is the donor atom. So this is the order, right? This will be the order of delta O, and that's why for this question also what will happen is, for CrCl6 whole 3 minus, it will be the maximum. Then ammonia is a stronger field ligand if we compare it with water. So this, and water is the most weak field among the given options. So this will be the order. Here we have to find out that Cn is having maximum, then NH3, then H2O. So option number A is the correct option for this question, question number 15. And also, I have told this before that why this CN or pi acceptor type of ligands are stronger field ligands than only sigma only type of complexes or halides. So what happens is, where because of this, we are having T2G orbital and EG orbital. For halides, what happens is we are having filled electronegative ligand. So that's why they will lie low in energy and it will generate this Eg will be same. Okay. This is T2G and these are the ligand orbitals. So this T2G is pi type, is having pi type character, and EG is having sigma type character. Now because of filled p orbital electrons in the ligand for case of halides, this T2G will interact with the ligand orbitals and it will give rise to one antibonding and one bonding set of orbitals. Okay, so this will be T2G and this will be T2G star. Now, as T2G star is lying uh, like closer in energy with this metal T2G orbital, therefore this will be highly metal based and this will be the new HOMO, and the energy difference between T2G and EG will be this. Whereas for complexes in which there is only sigma type of interaction, the del O value is this much. So we can see that on going from just sigma only type of interaction, which is seen for water and ammonia kind of ligands, to uh, any halide type of ligand where it is a pi donor, the delta O value is decreasing. Whereas if we have pi acceptor type of ligands like Cn or Co, as they are having empty pi star orbital, that's why the pi star orbital of ligand will lie here, and again this T2 metal T2G and ligand empty pi star orbital, they will give rise to one, the set of bonding and anti-bonding orbitals, okay, which is T2G and T2G star, and this is EG. So in this case, okay, this drawing is should be here. So in this case, what happens is this T2G will lie close in energy with the metal T2G orbital, and hence this will have more metal-like character, and this will be the new HOMO. So from T2G to EG, the transit sorry, this T2G will be above. Okay, sorry, this is T2G star. So now this is the new delta E or del O, that is the crystal field splitting. So therefore, on going from sigma only type of interaction to pi acceptor ligands, the del O value increases. Okay, so this is the reason behind that. But from spectrochemical series, if you remember the spectrochemical series, you can easily answer these type of questions. Was this question clear?
Yes, ma'am. Yes, ma'am.
Okay. So we will move on to the next question, which is question number 17, asked in question in GATE 2018. The question is the bond angle titanium carbon carbon. That is, they are talking about this bond angle titanium carbon and carbon. This bond angle in the crystal structure of the given complex is severely distorted due to what? So we have to answer why it is having a distorted bond angle. So the options which are given for this question is hydrogen bonding interaction, option number B, agostic interaction, option number C, steric bulk of the phosphine ligand, and option number D, higher formal charge on metal. So what is, among the given four options, what is the reason for this distortion in the bond angle? So we know that we all should be familiar with beta hydride elimination. Are you guys familiar with beta hydride elimination? Hello?
Yes, ma'am. Little bit.
Yeah. Yeah, so in beta hydride elimination, what happens is we have one metal, and then in beta position to this is the alpha position, this is the beta position. If there is a hydrogen present, then this hydrogen will go here and this will be like this. So will form MH, that is metal hydride, and ethylene. Okay, so that's why wherever if we have a complex where beta hydride is present, those complexes are not stable. Okay, they are very prone to undergo beta hydride elimination type of reaction to generate metal hydride and one olefin. So in this case also, if we see, this is a titanium complex and it is coordinated with this ethyl moiety. CH3, CH2, CH3 group is there. So this CH2, CH3 we can write as this CH2H. They have written like this. So this is the beta hydride, right? This is the alpha position and this is the beta position. So this H is present in beta position to this titanium. And in this case also, this thing can take place, right? So whenever there is a beta hydrogen present, then this interaction between the titanium and hydrogen, there is some sort of interaction between this titanium and hydrogen, and this interaction is known as the agostic interaction. The name of this interaction is agostic interaction. Okay. So if a hydrogen is present in the beta position, like not in the beta position, if the hydrogen is present, which is like attached to a carbon of beta position, then there is a certain type of interaction present between the metal and that hydrogen. That interaction is known as agostic interaction, and it leads to the final cleavage of this bond and formation of titanium hydride, like the metal hydride complex, along with the formation of an olefin. So the correct answer for this question, that is question number 17, is option number B, that is agostic interaction. The other options which are given is hydrogen bonding interaction. So what is hydrogen bonding interaction? We have hydrogen and there should be one electronegative atom present, right? This is the condition for having hydrogen bonding. But here if we see titanium, titanium is electropositive. It's nowhere electronegative. So it is an electropositive element, it's a metal. So the hydrogen bonding, there is no hydrogen bonding interaction. The next thing is steric bulk of phosphine ligand. So steric bulk is not playing any role here because it is like there is no steric hindrance for this hydrogen. Uh, like, and the other one is higher formal charge on metal. So that also don't have anything to do with this interaction between titanium and hydrogen. So the correct option is agnostic interaction. Is it clear?
Yes, ma'am.
Now we will discuss question number 12 from GATE 2018 paper. The question is, based on Wade's rule, the structure type of B5H8 minus is option number A, closo, option number B, nido, option number C, arachno, and option number D, hypo. So what is the structure type of B5H5, B5H8 minus? Anybody knows what does Wade rule states? We have discussed this type of question before also. So, okay, I am saying if we are having BNHN type of compounds, okay, BNHN and there is some X minus. Let's say we are having this type of compound. Then, if the compound is having BNHN 2 minus, then the structure type is closo. If we are having BNHN 4 minus, the type is nido. We are having BNHN 6 minus, then it is, yeah, hello, hello,
No, ma'am. Arch.
what?
Telling that type, ma'am. Arch, no.
Art, I did not get it, what?
Nothing, ma'am. Nothing.
Okay. So BNHN 2 minus is closo, BNHN 4 minus is nido, and BNHN 6 minus is arachno. Now the question in this question, it is B5H5 whole minus. So how we can write this complex is B5H8 minus, right? So B5H5 and 8 minus 5 is 3, right? So if hydrogen is going out, that means it will leave a charge of minus on the complex as it carries a charge of plus 1. So here how we can write this B5H5H8 minus is there is already one minus charge and then more 3 minus charge will get attached will come here. So it will be a B5H5 4 minus type of complex. So what is the structure of this complex now?
Nido, ma'am.
Yeah. So for this question, that is what is the structure type of B5H8 minus based on Wade's rule? So option number B, that is nido, is the correct answer. Is it clear? Someone was saying something. Or was there any doubt? Hello? Hello?
No, ma'am.
No
No.
doubt, ma'am.
Okay. Moving on to the next question, which is question number 13. Here the question is the coordination geometries around the copper ion of plastocyanin, a blue copper protein, in oxidized and reduced form respectively are option number A tetrahedral and square planar, option number B square planar and tetrahedral, option number C distorted tetrahedral for both, and option number D ideal tetrahedral for both. So, plastocyanin is a metalloprotein. This metalloprotein is present in chloroplast and it helps in the process of photosynthesis. Okay. So, plastocyanin, the it is a type of blue copper protein, and the function of this is electron transfer. It helps in photosynthesis. So, you should remember this, because many times they will give questions like match the following and they can ask that what is the function of this metalloprotein. So you should know that this is an electron transfer protein which helps in the process of photosynthesis and it is present in chloroplast. Now coming to the structure of this complex. For answering this question, we should know what is the structure of plastocyanin. So the structure of plastocyanin is that it consists of a metal center which is copper, and this copper is coordinated to four ligands. One is S sulfur from amino acid methionine. The other one is nitrogen which comes from histidine residue of the protein chain. It is coordinated to another sulfur which is a cysteine residue, and a nitrogen which again comes from histidine residue, and it can be present in +1 or +2 oxidation state. So we are saying that it helps in electron transfer, so it can go from +1 to +2 and +2 to +1, so it helps in doing that. So for +2 copper +2 compound also, it is coordinated to the same thing from methionine and from histidine, S from cysteine, and N from histidine. So we can write here that this is the reduced form and this is the oxidized form. Helps in electron, one electron transfer. Okay, so in both the two cases, like here, this copper one, it is a D10 system because electronic configuration of this is 3D10, 4s, 1. Now, since in this case copper is present in +1 oxidation state, so it is a D10 system, whereas for this the oxidized form, copper is present like, sorry, it is 1. So copper +2, here it was copper +1. So copper +2 is the 3D9, that is D9 system. Okay. So, and yeah, so the main question was that what is the coordination geometry of this? So here four ligands, it is coordinated to four atoms and it is having a distorted tetrahedral, like the distorted tetrahedral. We call this distorted tetrahedral, or also in some places we also call it flattened tetrahedral geometry. Okay. So this is the geometry for both the, we can see that the geometry remains same in both the complexes, right? Geometry remains the same. So in both the cases, the geometry is distorted tetrahedral or flattened tetrahedral only. So I told you the other facts because in, like, you might come across questions in which the other things are asked, like what is the function of it, or why. Maybe they can also ask that this is not colored but this is colored, something like that. For that the option will answer will be because it is a D10 system, whereas this is a D9 system. D10 system means it is completely filled. So that type of question might also come. So you should know a little bit about plastocyanin. But for this question, that is what is the coordination geometries around the copper ion of plastocyanin, a blue copper protein in oxidized and reduced form respectively, is tetrahedral and square planar? No. Square planar and tetrahedral? No. Distorted tetrahedral for both. So this is the correct option. Ideal tetrahedral for both? No. So is it clear?
Yes, ma'am.
Yeah, so today five questions are
Ma'am,
already solved. Yeah.
why it is distorted tetrahedral, not ideal tetrahedral? What's the
I
reason?
maybe because of the protein, like protein ring, the peptide ring with which it is connected, it can't be present in that perfect 109.20 minute that angle. Feel it. It's because of that peptide chain, that the protein chain which is present across it. That will be the reason. Because it depends on like what is coordinated to this metal centers, right? That decides what will be the geometry of the complex. So maybe it is not present as like it is not showing an ideal tetrahedral structure because of this protein chain which is present with this IT, because they have studied this. So option will be that only. Now I don't know the complete structure of plastocyanin, but if we see, maybe it's arranged in such a fashion that the copper can't be in a proper can't maintain a proper tetrahedral geometry. So it is having somewhat distorted angles and hence this distorted tetrahedral geometry. This is something which we have to like remember.
Okay, ma'am. That's for because it is looking like tetrahedral, na?
Yeah, yeah,
So I
but
was asking.
no, I if we draw the protein chain will be a big one, right? It's not a
Yes,
small
ma'am.
molecule. So that will only dictate the geometry of the central metal which is present.
Yes, ma'am. That's why I was asking for reason, na? So it will be the
Yeah,
protein chain.
yeah, yeah, yeah.
Okay, ma'am.
Any doubt? Any other doubt? So today we finished five questions before 1 hour only. Is there any doubt in any question? And how are your preparations going on?
Ma'am, like you have shared the recording links already, na?
Yes,
I
yes.
want to ask if any problem arises and I comment there, will you reply there?
In YouTube channel?
Yes, ma'am. Will
Yeah,
you
yeah, I
reply
will
on that
reply.
channel?
Yes, I will reply on that, but like you can also mail me directly.
Okay, okay.
If
Ma'am,
I miss
actually,
out,
I was absent, I think, for 2 weeks consecutively now. So I had to watch that lectures.
yeah, yeah, you can watch that surely, and if you have any doubt, then you can comment there. Or also, this is my mail ID where you can mail me. I will definitely
Okay.
answer. Okay.
Thank you so much. It was a nice session.
Yeah, thank you. So, maybe we can take up one more question. I will wait.
Ma'am, if there is extra time, can you tell us something about spinals?
About spinners.
Spinals.
Yeah, yeah,
Yes,
yeah.
ma'am, spinals.
Okay. So, right here, spinners. So, this is for compounds which are having AB to X4 type of compounds. Okay. Where A is a divalent metal, B is a trivalent one, and X is oxide or sulfide, these type of ligands. Okay. So mostly we see the like X as oxygen and sulfur. O2 minus, H2 minus, and A2 plus is divalent, whereas B3 plus is trivalent. Now, as we know, like we should know this that in a crystal lattice, the metals are present in the voids, whereas the ligands are present in outside, right? So the void can be a tetrahedral void or an octahedral void. So the structure of like the three different type of spinels we can have. One is normal spinel, one is inverse spinel, and we can also have mixed spinels. Okay. So it will be normal, inverse, or mixed. This depends on whether this A2 plus and B3 plus this is present in the tetrahedral void or octahedral void. If A2 plus is present in tetrahedral void and B3 plus is present in octahedral void, then the structure will be it will be normal spinel.
Repeat last line.
Okay. So if A2 plus, that is the divalent cation, is present in the tetrahedral void, whereas B3 plus, which is the trivalent one, it is present in octahedral void, then we get a normal spinel structure. Okay. But if we have A2 plus present in octahedral voids and B3 plus is present, half of them are present in octahedral and the other half is present in tetrahedral, then the structure which we get is inverse spinel. And if we have a structure in which it is mixed, like it is in some places it's normal and it's inverse, the mix of that is mixed spinel. So now how we will find out that a complex is normal spinel or inverse spinel? That we can find out by using CFSE. So now what is CFSE? CFSE means crystal field stabilization energy. Crystal field stabilization energy. Okay. So in an octahedral complex, if we take one octahedral complex, okay. So We are having T2G and EG, and this gap is 0.4 dq, sorry, 4 dq or 0.4 del O, whereas the energy gap from EG to this is 0.6 del O, and CFSE is mod of number of electrons which are in EG, electrons in EG, and plus electron in T2G. So for each electron in T2G, we will take minus zero point 0.4 as it is lying lower to this, so minus 0.4, and for this we will take plus 0.6. Okay, so for we can take one example. Let's take Fe3O4. It will be easier to understand this. Okay, so in Fe3O4, the divalent cation is Fe2 plus and the trivalent is Fe3 plus. Now, Fe2 plus means it is having how many electrons in d orbital? Anyone? D6,
GD6.
right?
D6.
Yeah. So 1, 2, 3, 4, 5, 6, and Fe3 means it is a D5 system. 1, 2, 3, 4, 5. So if we calculate the CFSE value for both, like for this complex, then for Fe2 plus it will be, there are 4 electrons, 4 into minus zero point 0.4 del O plus 2 into zero point 0.6 del O and mod of this. So 4 4 16, it will be minus 1.6 plus 1.2 or minus zero point 0.4 del O. Okay, so it is stabilizing the energy orbitals. Whereas if we see Fe3 plus case, there are 3 electrons in zero point 0.4 and 2 electrons in zero point 0.6. So it is minus 1.2 plus 1.2, that is equal to 0 d del O. The condition is that we have to just remember this thing, that if CFSE value of A2 plus octahedral is greater, that is more stabilizing. Here it was 0.4, right? Mod of this means 0.4. If the value for A2 plus octahedral is more than B3 plus octahedral system, then the system will have an inverse spinel structure. Whereas if we have the opposite one, that is, if it is CFSE of B3 plus octahedral is more than CFSE of A2 plus octahedral, then we will get a normal spinel structure. And the few other points which we have to remember is, for non-transition elements, the CFSE value is 0. For non-transition elements, the CFSE value will be 0. So if we are having a structure like, how to say, there was one, if you take out questions, you will understand that sometimes there will be options given like, there will be one non-transition metal and the transition metal. So you have to compare. For non-transition metal, the CFSE will always be 0, and for the transition metal, you have to calculate and then see whether it is satisfying this inverse spinel structure, inverse spinel like condition, or normal spinel structure condition. Now, one question which you will have, that then when we are getting mixed spinels. So if we have complexes which have comparable size, let's say there are few examples of this only. Like if we take this example, manganese Fe2O4. Okay, so in this compound, but manganese is this. There was one option. I am giving you this option also. Let's see. Manganese is present here in 2 plus. So manganese 2 plus means it is a D5 system, and Fe is 3 plus, so it is also a D5 system. So in both the cases here, CFSE value is 0. Now how we will compare this complex? Since manganese and iron 3 plus, manganese 2 plus and iron 3 plus, they are having a comparable size. Therefore, we can't differentiate on the basis of size as well, and we will have mixed spinner structure. Whereas if we have Zn Fe2O4, so
Ma'am,
in
please
this case,
repeat.
yeah, I am saying I will tell this Zn one also, then I will compare these two. Why I said about these two examples. So zinc 2 plus is, it is a D10 system, so CFSE for zinc 2 plus is 0 and Fe3 plus is also 0. But in this case, we will get a normal spinner structure. So these two examples you should know because it is very common in the given option. So we can have, when I say that, normal spinner structure or inverse spinner structure. Now what we will do if for both the trivalent and tetravalent metal, for both the CFSE is coming out to be 0, then how to compare that? Okay. So now, as I said, the structure, this depends on whether it is present in tetrahedral void or octahedral void, and tetrahedral void is smaller than octahedral void. Now, if the smaller metal, okay, if the smaller metal ion is present in the smaller void, that is, if it is present in tetrahedral void, and the larger one is present in the octahedral void, then we will get a normal spinner structure. Whereas if the opposite thing happens, then it will be inverse. Okay, so in this case, what is happening is in Zn Fe2O4, for both the CFSA is coming out to be 0. But why we are getting normal structure, normal spinner structure? It is because we know that if we go across a period, like the size of the metal ion decreases, right? So Fe will lie here, and after that cobalt, nickel, and then this will cobalt, nickel, copper, and then zinc comes, right? So zinc is having a smaller structure than iron, and here it is going to the tetrahedral one. Like this is the Zn2 plus one. This is the divalent one. So since this is smaller and this is occupying, it will be occupying the tetrahedral void. That is here A2 plus is occupying the tetrahedral void, and Fe3 plus it is occupying the octahedral void. So it is satisfying this condition. So it will show a normal spinner structure. Whereas if we take another example in which again for both of them, it is both are having 0 CFSE value, but here in this case, we can't compare on the basis of size, right? Because manganese and iron, they are of comparable sizes. So in this case, since we can't differentiate them in any other means, so they will have a mixed spinner structure. Okay, neither completely normal nor completely inverse. They will have a mixed spinner type of structure. Was it clear?
Ma'am, please repeat the case of MnFe2O4.
Okay. So for this, you should have few points in mind. One is if both are transition elements, then you can compare this like if A2 plus octahedral is having a higher energy, then B3 plus octahedral, it will have inverse spinor structure. If B3 plus octahedral is having higher CFSE value than A2 plus octahedral, then you will have normal spinor structure. And then comes the case where for both A2 plus and B3 plus, the CFSE is coming out to be same. Okay, in like the example is ZnFe2O4 and MnFe2O4. So for both these cases, the CFSE value for both the divalent and trivalent complex is 0. So now how to compare them? So we are having two type of voids where metals are present, tetrahedral or octahedral. Tetrahedral void is smaller than the octahedral void. If the divalent, like if the smaller one is present in tetrahedral void, which is here in this case, Zn2 plus is the smaller one and A2 plus, so it is present in the tetrahedral void. The divalent one is present in the tetrahedral void and the trivalent one is present in octahedral one. Zn size is smaller than Fe. So Here A2 plus is going to tetrahedral and D3 plus is going to octahedral. So normal spinel structure. Whereas for MnFe2O4, everything is same. But here we can't separate, like we can't compare their sizes because manganese and iron, they are having comparable size. So therefore, in this case, it will show a mixed spinel structure. This is the complete thing.
Okay, ma'am. Thank you.
Okay.
Yes,
Anything else?
ma'am. Thank you.
So you
Ma'am,
can take up a few questions from this. Actually, in last class, I have also solved a question from this. You can watch that video. And if you have any doubts, you can get back to me.
okay, ma'am. Ma'am, actually, I have examples also. I will try today only. If any problem, I will mail you.
Yeah, sure. Okay,
Thank you so much, ma'am.
okay. Okay then. Bye.
Bye.